logic of quantify statements actually. So let's just admit whoever is joining, okay, in the lobby. It's recorded already, right? It's recording. Okay, so let's have the logic of quantify statements. I cannot write anything. What's happening here? Okay. Cannot write anything. Stop. Okay. So this is what we discussed last time actually, using these connectives. This can be used only to identify the truth values of the statements. For example, not true is equal to false, not false is equal to true. Or if you have true or true is equal to true. And if you have T, then F is equal to F. So these symbols can be used only to identify the truth values of the statements. This cannot be used to identify, for example, whether the argument is valid or not, like this. This is an example of an argument, and to identify whether it is valid or not, we don't use this operators not, and, or, if then, if and only if, and exclusive or, because these symbols are only used to identify the truth or the falsity. Okay, it's all about truth or falsity only. Now, validity is different. This is what we talked about last time. Validity is all about identifying the argument, whether it is valid or not, by separating the parts. Like all men, this is A, and mortal is B. You remember? So we have all men are mortal. Our A is all men, and B is mortal, right? Socrates is a man. So Socrates is C, man is A, because it is part of all men. Therefore, Socrates is mortal. This is C, mortal is B. So this is an example of a valid argument. It follows A, B, C, A, and C, B. Okay? We just remind other students to join us now. It's a problem we have to open from time to time. Where is this link here? Okay, so this is what we covered last time. This is about validity of an argument where we have to identify A, B, C, A, C, B, and only then we can tell whether it is valid or not. So in validity, what we did, we separated the statements into parts, okay? In much the same way that you separate declarative sentences into subjects and predicates. So for example, all men are mortal. This is actually the predicate, are mortal. And all men is the subject. Okay, this is the subject. Subject is what we are talking about. So this is what we did last time by separating the statements into parts. Now, what we're going to have today is to use all, some, for example, these are quantifiers, denoting some quantities. And I'm going to review some parts of deductive, inductive, and some other things. Okay? So what we are going to focus today are the quantifiers actually, which is part of your exam also, midterm exam. So what we did last time was propositional logic. Okay, when we had, for example, true or true is equal to true. Okay, when we connect statements and identify the truth value, that is all about propositional logic. For example, Dubai is the capital of UAE, or 1 is greater than 0. This statement is true, although the first statement is wrong. Dubai is the capital of UAE is false, or 1 is greater than 0 is true. Okay, true or true is true, false or true is also true, right? Dubai is the capital of UAE, or 1 is greater than 0. The whole statement is true because false or true is equal to true. What we did was all about propositional logic, identifying the truth values of the statements and propositional forms. Today we're going to have predicate calculus or predicate logic, where we use quantified statements. So predicate logic is actually symbolic logic, where we use symbols. We're going to translate English sentences, translate from English sentences to symbolic form. Okay, this is what we're going to cover today. We'll be changing from English to symbolic and symbolic to English. Okay, so let's start with predicate. Okay, as noted before, when we say he is a college student, it is not a statement. This is an example of a sentence which is not a statement. It is a sentence but not a statement because we don't know who is he. Unless otherwise we're going to define he is Abdullah, for example, Al-Mukaini. We define it, but we don't know. The pronoun he is used. He, she, it, they, all of these pronouns will give us a sentence which is not a statement. In the same manner, x plus y is greater than 0 is also not a statement, because we don't know what is x, we don't know what is y. But if I'm going to write like this, x plus y greater than 0, x is equal to 2, y is equal to 7, this will become a statement because we know exactly what is x and what is y. 2 plus 7 is 9, so it will become true. So when I say statement, it is any sentence that can be true or false. Okay? For example, instead of writing x plus y, I'm going to write 2 plus 7 is greater than 0. This is a statement, which is a true statement. If I'm going to change the numbers, okay, if I'm going to write -5 plus -6 is greater than 0, this is also a statement, which is a false statement, because -5 plus -6 is -11, which is less than 0. So now in predicate logic, usually what we do is to look at the predicate. So what is the meaning of predicate? Let's start with the English first. In grammar, predicate is actually any part of the sentence that describes the subject. It gives information about the subject. When I say he is a college student, this sentence, the subject is he. Subject is the one we're talking about. This is the predicate. Predicate is the information about the subject. So he, who is he here? He is the one who is a college student. So predicate is the part of the sentence from which the subject is removed. For example, we say he is a college student. If we're going to delete the subject, the remaining is the predicate. This is the predicate. That is another definition of predicate. Part of the sentence from which the subject is removed. And sometimes we don't remove all, we just remove some. Okay, let's take this example. James is a student at Bedford College. Who can tell me where is the subject there? James is a student at Bedford College.
James.
James, very good, is the subject. This is what we're talking about. Where is the predicate? This is the predicate. Is a student at Bedford College. That is the predicate. This is the part of the sentence that gives information about James. Okay? So in some cases, we can remove all. Like we can remove also Bedford College. So the remaining will become is a student at. Okay? This is the meaning of this, some or all the nouns. Okay? James is a noun. Okay? Bedford College is a noun. Noun means names, labels. So let's now start converting. Okay, let me just insert. Okay, let's go to the conversion. How to change? For example, usually we name our predicate using some letters. Is a student at Bedford College. This is your P. Okay. Now, instead of writing James is a student at Bedford College, for example, we say X is a student at Bedford College. So in predicate logic, our subject usually becomes a variable. It is open, like this, X. Okay, this is what we call as predicate variable. We will have an open sentence. This is an example of open sentence. It is open because we don't know who is X. It can be any student at Bedford College. It can be Mariam, it can be Muhammad, Ahmed, Christine. All the students at Bedford College will be part of this. So it's not only X. X here could be any student. And the P here is what we call as the predicate symbol. So in predicate logic, we usually use predicate symbols and predicate variable. Okay, so remember that. So how do we change this sentence into predicate form? X is a student at Bedford College. The predicate form contains two things: the predicate symbol and predicate variable. Two, always. Variable or variables, symbol or symbols. So as I said, we're going to change English to symbolic. So the answer to this is how you write in Arabic. We start from right to left. So X is a student at Bedford College. The subject will be inside. Then is a student at Bedford College will be outside. That is P. So P is outside. So we have P of X. Okay, so the subject is always inside. Then we go out. We write our predicate. This is our predicate. P is a student at Bedford College. Okay, so this is the answer. Let's have another one. For example, we say X is a student at Y, for example. Assuming that this is our sentence. As I said, we call this as an open sentence. It is open because our subject, we don't know, it is X, and here another noun, we don't know, Y. It's a student at any university, any college. It could be Majan University College, okay, Harvard University, any college here. X, any student. That's why it is called open sentence. Okay, so if you're going to change this, for example, Q is our predicate. This is our predicate. Is a student at. Okay, because we remove our subject and another noun, Bedford College, is removed. James is removed. We put X. Bedford College, we change it into Y. So, for example, our is a student at is Q. What is the predicate form? As I said, we're going to start from the inside. Our subject is X, then we go out. X is a student at Q, then comma because we have another variable at Y. Okay, so this is the answer. X is a student at, we go to the left, then we have to go to the right again because we have another variable. So here we have two variables, two predicate variables. Sometimes you have only one, sometimes you have two or more. So this is the answer. So the answer here for the first one is P of X. And here X is a student at Y is Q of X comma Y. Okay, so our P is a student at Bedford College, is a student at Bedford College. And our Q is a student at. We don't have Bedford College. So it becomes like this, the answer. X is a student at Y. Here, X is a student at Bedford College. We have P here because P is the symbol. It depends on the symbol given. So X and Y are predicate variables, as I said, and this can take values in appropriate sets. So this can be any value. Any student is X. Y here is any university or any college. When we change the X and Y with concrete values, it will become a statement. Yes, for example, I'm going to change X into the name of a student. It will become a statement because it will become true or false. Same here, X is a student at Y. I might say Muhammad Abdullah is a student at MUC. So we can verify that whether it is true or false, right? It becomes a statement. Okay, so I hope that is clear. Let's try to answer this for you to understand better. Now the given sentence is N is a fish. So that is our sentence. We're going to change to predicate form. Now F stands for is a fish. Usually we use the first letter, but not always. So how do we change this? N is a fish. There are still many students trying to join. Okay. Now, as I said, we're going to start from the inside, N, then we have to go out. N is a fish, that will be outside, F. So the answer is F of N. Now let's have this one. G is greater than, is greater than. Now what is the predicate form of M is greater than K? We're going to change this to predicate form. So we start from the inside. M is greater than, the letter is G, is greater than what? Than K. So these are the answers to these questions.
Mister, can you repeat again?
You just follow from right to left. Right to left. Like how you write in Arabic, right to left. Yeah, so for example, N is a fish. We start from right to left, like this. N, the starting is N, so start from N. Inside. Is a fish, we have a letter. What's the letter for that? F, right? So we put F here. Right to left. For example, when I say K is a monkey, where do you start writing? For example, is a monkey is M. So what is the answer? K is a monkey. Anybody?
M, then we put K
MK.
between the brackets.
Yes, K is a monkey. This is the answer. Do you understand now?
Yes.
So here we have M. M is greater than K. So we start with M is greater than, that is G. So G, comma, K. We put comma because we have two variables, M, K. Is that clear?
Clear.
Okay, so let's now proceed to the next. These are just very simple conversions. So as I said, when we change the variables, it will become a statement. For example, here, I'm going to give a type of a monkey. A baboon is a monkey. It will change. Here, we can change F, or our N, I mean. We can say shark is a fish. This is our N. So the N here can take any value. That's why it is open. Shark, catfish, milkfish, goldfish, any fish can be substituted here in N. Okay? So a predicate has predicate symbol and predicate variables. This is what I'm talking about. Any predicate form contains two things: predicate symbol and predicate variable or variables. Variable or variables. Like here, we have F and N. N is the variable, F is the symbol. Here, M and K are the variables, G is the symbol. That is the meaning of predicate form. It has predicate symbol and predicate variable. So as I said, we call this as open sentence. When you say N is a fish, is open because we don't know what is N. We can put any value. Or we call this as propositional function. Yeah? It is a function because, for example, here, f of n, we can put any, we can input any value for n and it will give us an output. So it is a function because n can take any value, catfish, goldfish. So every time we change n, we will have a different output, a different sentence, right? So those that we put inside here actually are part of domain. For example, N is a fish. Our domain are any type of fish. Goldfish, catfish, shark, and any other types of fishes. That is what we call as domain. Okay? Set of all values that may be substituted in place of the variable is called as domain. In some cases, we cannot write all the domain, like N is a fish. We cannot write all. We can write some examples only, like what I did. Yeah, because we cannot write all the types of fishes. In some cases, we can write all. Okay, we say N is a whole number from 1 to 5. So here our domain is finite. Finite means we can write all. Okay, we can know until where exactly. So here our domain is 1, 2, 3, 4, 5. Just from 1 to 5. Here n is a fish, it is infinite. The values for n are infinite. It will not stop. We cannot write all. It's impossible to write all. Yes? Although, in theory, yeah, if you are a scientist, for example, then you can, if you have all the types of fish, for example, but it keeps on, but until now, there are so many fishes under the ocean that are not yet discovered because it's so deep, There are some fishes there down, deep down, which until now are not yet discovered by scientists. So it's something infinite. Okay, so let's now proceed to identifying the truth value. Because as I said, you can identify whether it is true or false if you change the variable. For example, our predicate form is x squared is greater than x. This is our variable. As I said, the variable can be changed. It will become true or false. Like n is a fish, our variable is n. If we say a catfish is a fish, it becomes true. Here we don't know whether it is true or false because it is n. Here we have x squared is greater than x. X is our variable. For example, we talk about real numbers, r. R means real numbers. Any number that can be represented on the number line. Any number on this line is a real number. Negative numbers, positive, and decimals. So, for example, the given numbers are 2, 1/2. We have negative 1/2. For example, these are the numbers. Okay? Because the given is p of x is x squared greater than x. Okay? So we can test these values. Real numbers, we cannot write all. There are so many. So we can just try some values. 2, for example. So if it is 2, it will become 2 squared greater than 2. 4 is greater than 2. It is true. Okay. Now let's try 1/2. 1/2 squared is greater than 1/2. 1/4 is greater than 1/2. This is false. Because see, 1/4, 1/2. 1/4 is 0.25. 1/2 is 0.5. If you have p of negative 1/2, negative 1/2 squared greater than negative 1/2. So this is 1/4 is greater than negative 1/2, which is true. Because any positive number, 1/4 becomes positive because negative 1/2 times negative 1/2. It is greater than negative 1/2. So how many true do we have here? We have 2, this and this. Okay. And we have only one false, this one. 1/4 is greater than 1/2. This is what I'm talking about. Every time we have some values in our domain, we will have true or false statements. Okay, so is there any question here? Now, the values that make the statement true are part of the truth set. Okay. Here, the values that made our statement true are 2 and negative 1/2. Okay, so our list is 2, 1/2, and negative 1/2. Okay, our truth set contains 2 and negative 1/2 based on these given examples. Because when we substitute 2, it becomes 4 is greater than 2 is true. Here, when we change x to negative 1/2, it becomes 1/4 is greater than negative 1/2. It is true also. So there are two values amongst these three which made the statement true. So it belongs to the so-called as truth set. Truth set means the set of numbers that makes the statement true. Okay, so that's what we call as the truth set. Set of all elements that make the predicate true is called as the truth set of the predicate. Okay, so usually we follow this method of writing. So let's look at this. What's the meaning of this? So this line in the middle is called as such that or given that. Okay, x is the variable and D is the domain. You know already what is domain, set of all possible values. E, of course, is in. Okay, inside, element of. That means element of, for example, A is equal to 5, 6, 7. 5 is an element of A. 6 is an element of A. 7 is an element of A. So element means it is inside the set. Okay? So 5 is inside set A. 6 is inside set A. 7 is inside set A, right? So that's the meaning of this symbol. We just call this as is inside. It's inside the domain. So X in the set of all. Set of all. So whenever you see these brackets, it means the set of all. That means including all the elements that we talk about, the domain. Okay, whatever we're talking about. X could be, the variable, and the P here is what we're talking, the predicate. So we say X is a student at MUC, Majan University College. So our domain is the set of all students, all the students at Majan. Business students, IT, English foundation, all. Set of all. That's the meaning of this bracket here. These two brackets mean that we include all of this domain. Okay, our domain here is, our D is all students at MUC. If you're going to say X is a student at MUC. So I hope you understand the meaning of domain. Okay, domain is the set of all possible values, what we talk about in our predicate. When I say X is a monkey, so X is all about monkeys, all monkeys. So our domain here is set of all monkeys. It could be chimpanzee, gorilla, baboon. Okay, a baboon is a monkey. Yes, there are so many types of monkeys, right? This one is the baboon. We have also chimpanzees. They look different. Gorilla. They look, of course, they're so huge, so big. So this is what I'm talking about. Domain is actually what we are talking about in our predicate. Set of all possible values. When you say N is a fish, we talk about fish. That's our domain. X is a student at MUC. We talk about students. Students are the domain. Okay, so let's look at these examples. Letter A, the domain of N. Okay, so we are going to find the truth set of Q of N. If the domain, letter A, the domain of N is the set Z plus of all positive integers. Z plus means positive integers. This one. Z minus means -1, -2, -3, dot, dot, dot. Z is higher. Z minus and Z are part. This is Z minus. This one is Z plus. And we have the 0. So there are 3 parts in Z. Z means integers. Integers have 3 parts, the 0, positive numbers, Z plus from 1, Z minus from -1 to -infinity. So Z plus and Z minus are part of integers. N is natural numbers or counting numbers. From 1, it is equal to Z plus. Same. Okay, so the domain of N, so we have Q of N is a factor of 8. That is our, so basically, how do we say this? N is a factor of 8. So where is our subject here? We have the N. N is our variable. It is our subject. This is our subject. This is our variable, right? So the symbol is given already. Q of N. That means this is our Q. This is our Q. Because we start writing from inside. So N is a factor of 8. So is a factor of 8. This is Q. Yeah. Is a factor of 8 from here. That's Q. N is the one inside. Inside the parenthesis you can see here. And is a factor of 8 is Q. Is a factor of 8. So in some examples, it is given already like this. A predicate form, Qn. Okay, so what are we going to do? N is we're going to follow this X element of D. So instead of X, we're going to use N element of N. So NQ. So what is our domain? Factor of 8. Such that it is what? N is the set of Z plus. So we are following this. We have x element of the, instead of x, we are using n element of, what is our domain? So we will be changing this to our domain. Sorry for that. Our domain is z plus, right? Z plus, and here will be our predicate. So in this particular symbols or set, we usually write our predicate at the end. This is our predicate form, which is given already. Okay, and this open and close is always there in the beginning, open and close. And qn is after the line. After the line is the predicate is already given here. Okay, so please remember that. And this n, whatever is the variable, here the variable is x, but here the variable is n. N is a factor of 8, so we have n here, not x. This will not change. This is the domain. Our domain here is D. Here, what is our domain? The domain of n is the set z plus. So it becomes z plus. Okay? So what is the answer? What's the answer of this? Z plus is our domain. As I said, this is a z plus. And we need to find factor of 8. So you know, factors means the number that we multiply. So 2 times 4 equals 8. 8 times 1 equals 8. The factors are, so the answer is 1, 2, 4, 8. This is the answer. Because 1 times 8 is 8. 2 times 4 is also 8. So these are the factors, because we are allowed to use only positive from 1, 1, 2, 3, and so on. So 1, 2, 4, 8 only. So these are the elements inside our truth set. Okay, using the Z plus as the domain. Let's answer letter B. The domain of n is the set Z now of all integers. In the first one, we have Z plus. Here we have Z. So what will be our answer? Let's answer letter B. Letter B is we have set of all n in Z, because our domain equals Z. Okay. Such that our predicate, this is our predicate. Okay. So don't forget, when we talk about truth set, we have to put open and close. Open bracket, close bracket. Because the question is find the truth set. Okay, so that's why we have here open and close, and then the variable. What is the variable? N. In. Element of, what is the domain? Domain is Z. And then line, whatever is the predicate that we're talking about. Predicate is Q of n, that is n is a factor of 8. This means n is a factor of 8. So using the Z, what are the factors of 8 using this? 8 can be 1 times 8. 8 can be negative 1 times negative 8, because negative numbers are allowed. 2 times 4. 8 times 1, negative 1 times 8, 2 times 4. What else? Negative 2, negative 4. Yes? So the answer is 1, 2, 4, 8. -1, -2, -4, -8. Okay, open and close. Do you have any question here? Guys?
Clear, Mr.
Okay. So here the answer is more. You have 1, 2, 4, 8, -1, -2, -4, -8, because Z is the domain. So the domain will tell you how many elements are there in the truth set. 1, 2, 4, 8, -1, -2, -4, -8. Okay? Now let's proceed to the quantifiers. We have, as I said, all and some as the most common ones, but I'll be giving you other words to be used. These are introduced by these two guys, Charles and Gottlob. They started in the late 19th century. So let's start with the first one. All human beings are mortal. How do we change this into a predicate form? This is the English. English is informal. Okay, in predicate logic, English is informal, and the predicate form is the formal language. So, for example, all human beings are mortal. The first thing you're going to do is to change the domain into a variable. So here we talk about human beings as our domain. So let age equals set of all human beings. Okay, set of all human beings. So to change that, we are going to follow this form. Okay, comma q of x. So the symbol is this. If it is all, every, each, any, anything, everything. Whenever you see these words, you are going to use this symbol, like inverted A. Okay, so the answer is this. All, for all x in the domain. Okay, so x here is any variable. Whatever is used there, it should be same here. If this is n, this should be n here. So to be safe, use x. So x here is part of this domain. So the domain is, what is our domain? For all x and d, q of x, this is the main form. This is the main. So the answer will be in h, because our domain is h, comma, yeah. We have r mortal. So we say x is mortal. This is our q of x. If it is given, then you write like this. But we did not, we don't have the symbol for r mortal. So we just write x is mortal. So as I said, whatever is the letter here, it should be same here. And usually we use the singular. X is mortal, X is human, okay? X is a fruit. It depends on what is given. So please take note of the main form for universal. We call this as universal quantifier. Universal because we include all the elements, like all human beings, not only one, all. So it is universal. Let's answer another one so you will understand better. Here the answer is this, using the general form. This is the answer. General form again is this, comma, q of x. This is the predicate. Okay, domain you know already. For example, here, express in formal language. Formal means predicate form. All fishes can swim. So the English sentence is all fishes can swim. We don't care whether this is true or false. Now the answer, predicate form, follow the original. Okay, let F equals set of all fishes. This is the first step. You have to define the domain. What are we talking about here? Fishes. So the answer will be like this, for all x in F, like all fishes, comma, our q of x will be x can swim, because this is our predicate, can swim. Okay, so whatever is the letter here should be the same here. Any question here? Guys, do you have any question?
No, sir.
Okay, let's have this. If you have two variables like this for all real numbers, there are two variables x and y, comma, x plus y equals y plus x. This is actually true. For example, 2 plus 3, this is your x, this is your y, equals 3 plus 2, y plus x. Even in multiplication, 2 times 3 equals 3 times 2, 6, 6. Here we have 5 equals 5. Yeah? So we call this as commutative property of real numbers. This is all about commutative. X plus y equals y plus x for any real numbers. Look at the symbol here, already is given. When you see this symbol, it means for all. For all real numbers, x and y, x plus y equals y plus x. So how do we change this into predicate form? To change this in predicate form, let me show this in different slides. Okay, this is the given. English for all real numbers, x and y, x plus y equals y plus x. So the keyword here is all, for all. Okay, so we have to use this form. Okay, so for all, the answer is here. Because of the word all, we're going to use this symbol, x. We start with the first variable because there are two variables, x and y. In, okay, what is our domain? What are we talking about? Real numbers. Real numbers is R. Okay. For all x in R, okay, and we have and here. So for and, what we're going to do, we are just going to put an open parenthesis here, because we are going to complete x and y. So again, you repeat For all y, the same, in the same domain, like this. So this is like and here, open. For the second variable, we have x is the first, y is the second. This is the first, this is the second. And then open, this comma here, you can just put open, whatever is the given property. This is the property given. Okay, property is x plus y equals y plus x, you close. This property should be one group. And we have to close this. So close. That's the answer. So this means that for all x and y, okay, which are real numbers, okay, something like that, because we have r. So for all real numbers, x and y, x plus y equals y plus x. That's how we write the answer. So see the answer here. For all x in R, open, all y in R again. We are just repeating this. Open the property. This is the property given. The property can change anytime. It can be x is equal to x, okay, or x squared is equal to x, or it can be two variables like this, x plus y equals x times y, xy, you know. So the property is here, which can change at any point in time. It can become like this, xy equals yx. So instead of x plus y equals y plus x, it becomes multiplication. X times y equals y times x. So that is just the property given here. This one is the property. So the property is inside the group. After defining two variables, the first variable and the second variable. Okay? So this is what I'm talking about. This is the general form of universal statement. Universal statement. For all x in D, comma, Q of x. The Q of x is the predicate. This is the domain. X can be changed. It can become like this. This will become n also. If you use n here, you have to use n here. It should be always same. For example, instead of x, you're going to write like this, m, okay, p. The domain is p, for example, comma, this will become q of m, because these two should be always equal, right? And the domain is what we are talking about. So this can only be true if all, okay, all or every x in D is true, okay? It is defined to be true if and only if Q of x is true for every x in D. That means if the predicate is true for every value in the domain, then it is true. Otherwise, it will become false. Let's have an example so you will understand. For example, our D is 1, 2, 3. This is our domain. Only 1, 2, 3. No 4, no 5, no 0. Only 1, 2, 3. Three numbers only. That is our domain. Now, this is our statement. For all x in D, because we have D here, same letter, this is our predicate. Our predicate here is x squared is greater than or equal to x. Okay, what is the meaning of predicate again here? Predicate is a sentence which is open with variables. That's it. Yeah, any sentence with variables. For example, X is a monkey. This is a predicate because we change our subject into a variable. Like here, X squared is greater than equal to X. Okay, X is any number here, 1, 2, 3. So that's the meaning of the X here. This X here below, when we write like this, the X here, that's why we say for all X in D, is any element inside this. So if our D is equal to 1, 2, 3, because you might be asking, what is this X here? So our X1 there is 1, our X2 is 2, our X sub 3 is 3. That's the meaning of this X. That's every element in this domain. So for example, our domain is MQR. Our X1 is M, our X2 is Q, our X sub 3 is R. That is the meaning of the X there. The X here is every element inside this. That's why we say for all X in the element of inside this. Okay, so this X here and X here are these numbers because this is the X, right? They are the same. So how do we prove that this is true? As I said, whenever you see this symbol, you have to prove all because it's for all. So show that the statement is true. We start with 1. X equals 1. So you try. 1 squared is greater than or equal to 1. 1 is greater than equal to 1 because 1 squared is 1. This is true because 1 is equal to 1. If X is equal to 2, you have 2 squared greater than equal to 2. 4 is greater than or equal to 2. So again, it is true because it is greater than 2. 3 squared is greater than equal to 3. 9 is greater than equal to 3. It is true. So this is indeed true. It is proven. Because when we tested all these numbers here in the predicate, after the comma is the predicate. The results are all true, 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 true. Okay, so this statement is true again because X is equal to 1 using this predicate. 1 squared greater than equal to 1. 1 is greater than equal to 1 is true. If X equals 2, 2 squared greater than equal to 2. 4 is greater than or equal to 2. Again, it's true. If X is equal to 3, 3 squared is greater than equal to 3. 9 is greater than 3. Again, it is true. Now, how to prove that it is false? To prove that the statement is false, if this is the symbol for all, we have to find one. That's why it's mentioned here, find a counter example that will show that the statement is wrong. Okay, so here, example. R is real number. So our domain here is not anymore 1, 2, 3. Our domain is any real number. So you have to look at the domain always. Here our domain is R. Here our domain is D. And D is given 1, 2, 3. We have proven. It's all true. Here, our domain is not D. Our domain is real number. So you are asked to find one example that will make it false. So let's try whole numbers, x equals, you can try. If it is 2, 2 squared greater than or equal to 2, 4 is greater than or equal to, it is true. So it's not working. We'll try some fractions. 1/2. So 1/2 squared is greater than or equal to 1/2. 1/4 is greater than or equal to 1/2. It is false. Yes, so we have. So therefore, this can be a counter example. Okay. This is the counter example showing that indeed there is a number that will prove that this statement is wrong. So it's very easy to prove that the statement is wrong if it is universal, like this, using this symbol. We have to find one only, at least one, to prove that it is wrong. But to prove that it is true is difficult. You have to prove all. You have to show all. Okay? So I hope this is clear. For universal statements, to prove that it is true, you have to test all. To prove that it is false, you have to find a counter example, only one, like what I did here. Let's now go to the existential. Existential means there exists. Okay, that means one or more, but not all. Not all. Okay. So for example, there is a student in math 140. How to change that? For example, the given is there is a student in math 140. This is the name of the module. Like LPSS in Philippines, in other countries, we use numbers like math 101. That's the name of the module. English 102. We usually use some numbers. In Oman, you just write LPSS, for example. I don't know with other universities, MSS, FBM, PCSE. Now, there is a student in Math 140. The keywords are this, there is. Whenever you see these words, there is, some, okay? Anyone is, someone I mean, anyone is for the universe. Someone, somebody, someone, somebody, okay? There is a, this is existential. You're going to use this symbol, okay? In the, such that, you're not going to use comma in such that, QX, okay? For universal, you are using this, comma, the predicate. This is universal. Existential, the comma will become such that. Okay, so you can let S equals set of all students, or you can use another letter if you want. You can use a different letter. So you write like this, the answer will become like this. There exists X. As I said, this X is any value in the domain. In domain, what is our domain? S. Because I define here set of all students such that X is a student in Math 140. Okay, so that's the answer. So instead of comma, we are using such that in existential. Let me give you another example so you will understand. For example, I'm going to say some. Okay? Some integers are positive. Okay? So what is our domain? Our domain, integers. That is Z, okay? Always remember that. The symbol of integers, Z. Real numbers are. Okay? And counting numbers, N. Counting or natural. Or natural. So here, some integers are positive. The answer will be answer for the predicate form. That means symbolic. You don't need to define because integers is Z. So there exists because some, not all. X in Z. Such that, okay, X is positive. So you have to change R, have, change to singular form. Because this one means every X, So that's how to change. This means some or there exists in an integer whose value is positive or such that that integer is positive. Okay, so that's it. This one is given already there, the symbol. There exists integers m, and so it's like some integers. There are two variables m and n such that m plus n equals m times n. As I said, we don't care whether this is true or false, right? So to change this into the symbol, how are we going to do that? There exists. Let me show you the answer because it might be confusing, right? So the given is like the sum integers m and n exist, okay, such that m plus n equals m times n. So this is the property given. So some integers, the symbol is given already. This is the predicate form I'm going to write here. Some. So here we're going to use, what are we going to use? We have m and n. So we're going to use m in z because integers. So these are the variables m and n, not x and y. Then comma, again for the other one, n, the same integers. Okay, so this means that there exists an integer which is m and n, or there are some integers m and n such that, okay, so usually we don't need to mention such that anymore because we have two variables. We have to put only the property here, m plus n equals m times n close, and we have to close this towards the end. So this is the answer. So as you can see, I repeated again the existential here and here because we have two variables m and n. So this is repeated, this and this. And m and n are there. And z repeated because m and n are integers. And then open and close the property. This is the property. Okay? So I hope this is clear. Did you get it? This is the answer. Okay, so as I said, we have to write there exists because it's given there anyway. M, element of integers z, or you can put a line here. And then again, you repeat this second variable and repeat the domain. And then write the property and close. And you have to close this towards the end. Okay, so this is the general form. As I said, you will have such that in the middle, not comma. For universal, you will have comma q of x. So to prove that this is true, we have to test only one. For example, here, there exists m in integers such that m squared equals m. Show that the statement is true. So if the symbol is like this, to show that it is true, at least one. Only. Because it means there exists. Okay, this means there exists. So there exists an integer, z is integer, such that m squared is equal to m. So integers are negative, 0, and positive. Let's try 0. 0 squared equals 0. 0 equals 0. Yes. You can try also 1. 1 squared equals 1. 1 equals 1. Yes. So there are two numbers there, in fact, when your square is equal to itself. So this statement is true because we have given some examples. Okay? Now here, to consider that this one is false, you have to check all. 5, 6, 7, 8, 9, 10 is our domain, such that m squared is equal to m. Show that this statement is false. We are saying that there exists m in P such that m squared equals m. But our P is not integer. Our P is 5, 6, 7, 8, 9, 10. Okay? So how to prove that? Let's use this. 5 squared equals 5. Wrong. 6 squared equals 6. Wrong. Because 6 squared is 36. 7 squared equals 7. Wrong. 8 squared equals 8. It is wrong. 9 squared equals 9. Wrong. 10 squared equals 10. It is false. So all, the whole list gives us false. So we have proven that the statement is false. This statement is false. Okay, there exists m in P such that m squared equals m, and P is from 5 to 10. So basically it depends on the domain. Our domain here is P. Here our domain is Z. Okay, Z, of course, we have some numbers that will be equal to its square. Like 0 squared is 0. 1 squared is 1. That's for integers. But here, only 5, 6, 7, 8, 9, 10, it will not give. Because 10 squared, for example, is 100. Okay, so I hope that is very clear. Let's have some examples how to change from symbols to English is the opposite. What we had a while ago, we're changing from English to symbolic. For example, all men are mortal. Okay, we say, for example, let M equal set of all men. We are changing from English to symbolic. So the symbolic or the predicate form will be all X in M, because men, X is mortal. So from English to symbolic. Now we have symbolic form to English. It's the opposite. So how do we do that? This is from formal to informal. When I say formal, this is predicate form. Informal is English form, English sentence. For example, this one. Okay, you start from left to right. This one is all. So all real numbers, because R, all real numbers have squares greater than or equal to 0. This is the answer. All real numbers, because R, and this is all, have, because you use all. You can use every, but this will become has. Every real number has a square greater than or equal to 0. Here, for example, all real numbers have squares not equal to -1. Okay, it's not equal to. And then here the last one, this one letter C, this one there exists. Or you can use some. If you're going to use some positive, some integers, because we have Z, have squares equal to itself. Because M is equal to M squared. Or you can use there exists an integer. Okay, so if you use there exists, it will become integer, singular. If we're going to use some, it's plural. Some integers have. Or you can say there exists an integer, it becomes singular. Whose, then we're going to use whose square is equal to itself. So it's up to you which one you're going to use in the exam. If you want to use singular or plural. Okay? So you can use, as I said, any method, but you have to choose only one. You can use also non-negative here, because greater than equal to 0 is non-negative. So you can use your own words. So these are the keywords for this symbol. Every, any, each, everything, anything, all. That's it. So here, all real numbers have squares not equal to -1. Or you can say no real numbers have squares equal to -1. It's the same meaning. So how do you use this method of expressing? For example, you say all human beings or all humans have no wings or do not have wings. You can use no in the beginning. Actually, you say no humans have wings. It's the same. All humans do not have wings. No humans have wings. Okay? It's the same actually. So this one, you can choose any. It is in the move page, but choose only one. Say there is an integer whose square is equal to itself. This is what I was telling. Or we say we can find at least one. You can also use this, at least one. This symbol is also at least one or more, but not all. Now, let's translate from English to symbolic. It's the opposite. We had a lot of examples a while ago. Yes? So opposite now. All triangles have three sides. So you can let T equal set of all triangles. So that is the first step you're going to do, define the variable. So answer for letter A, for all x in T, comma, x has three sides. As I said, plural will become singular. If it is R, it will become is. If it is have, it will become has. Okay, letter B, first define domain. D equals set of all dogs. Okay, now no dogs have wings. Change it to all dogs do not have wings, so you will not be confused. Change first into this form. When you say no dogs have wings, it means all dogs do not have wings. So the answer will be for all x in D, because D is set of all dogs, comma, x does not have wings. So it becomes singular, does not. Do not becomes does not. Okay. Let's now have letter C. Let P equal set of all programs. All programs. That is P. This one is let, L-E-T. So, what will be the answer? This one, because sum in P such that X is structured. Because mentioned, some programs are structured. So R becomes is. All right, so this is very, very clear. Before we're going to finish today, let me have for like 5 minutes some of these examples. This one I answered already. You can use small t instead of x. It's up to you, like this. Instead of writing for all x in T, x has three sides. You can use small letter t for all, okay, t, small letter t, and then big small letter t has three sides. Okay, it's also acceptable. Okay, instead of x, you can use small letter of this. Okay, I might be giving you in the test something like this. Say, someone, okay, cries and laughs. Okay, how do we change this into predicate form? This is informal. Change to formal. Formal means predicate form. or predicate logic. Okay, so the answer will be like this. Someone, so it will be like this. Okay, then open. Person, you have to define that someone is a person, X is a person, and so this is the connector. That person cry, okay, and that person laughs. So we have to close this, and I have to close this. Okay, so basically, this is a different way of translating. If we have like something like this, you know, like a sentence and a connector here, and this is the and. Okay, and this one, this and is to connect someone and this verbs. This actually is the predicate. This is the part of the sentence that describes someone. So we have here the whole group. Okay, this open and close is for X. Here we have open and close is for X. This close parenthesis is for this, because you have to close this. The partner is this. This, the partner is this. So you have to close. Whenever you open something, you have to close it. Let me give you another example. So you have to define first who is that someone. Okay? For example, you say some animals. Okay? Fly and talk. Some animals fly and talk, so the answer will be, this one is some. So there exists. Then you have to define animal is X. X is animal. And open, fly, X, and talk, X. Close and close. So always you have to use the base form of the verbs. For example, laughs. The base form is laugh. Talks. The base form is talk. Okay? So please use the base form of the verb. Another example. If someone cheats, he fails. So here we have if and comma. That means we have then he fails. But sometimes we remove the word then, it's understood. If someone cheats, then he fails. So that means the answer will become like this. Okay. And then person, that someone is a person, and okay, cheat, X, then fail, X. Okay. So this means if, because we have if then here. If a person or if someone cheats, then he fails. Okay? Do you have any question here? Guys? Guys, are you still there?
Yes, yes. No question.
Yes.
Okay. All students except Abdullah speaks. Or all students except Abdullah speak. Because all students, you know. So here plural. So what's the meaning of this? All students except Abdullah speak. That means everyone speaks except Abdullah, right? Abdullah is not talking. All the students are talking except Abdullah. So the answer, when you're asked to write the formal language is the predicate form or symbolic from English to this form. So all student is X. You have to define that. Okay, you have to always define the domain. And okay, X not equal to Abdullah, then speak X. So this means all students except, this is except, not equal to Abdullah speak. So it's like if, because we have then here. The best way to solve this is to put the if then. Okay, because if then actually is all. We say if a monkey, okay, if a student cheats, he fails. What's the meaning of that? It means that we are talking about all students. Example, if a student at Marjan cheats, he fails. Are we talking about one student only? Using the if? Because we have the if there. The if will transform the whole statement into all. All students actually, because of the word if, because you are assuming. It's like any student. It could be Mariam, Buthaina, any student. So here, we can use if then. If a student, okay, is not Abdullah, this is not Abdullah, then he speaks, okay? Something like that. So all students except Abdullah speak. Okay, so this is your homework. I'm going to give one homework. All animals except ostrich fly, for example. Okay. By the way, this one is false, you know. It could be false or true, but we don't care. So as I said, we don't care about true or false, but this statement is wrong. I want you to change this to predicate form. Okay, this is number 2. Number 1, some people sing and talk. Okay, so guys, we don't care whether it is true or false. As I said, we have just to change to predicate form. Okay, this topic is not talking about true or false. This is about changing to other forms. So there are 2 there. Some people sing and talk. All animals except ostrich fly. Change to predicate forms. Okay, can you please take a screenshot of that? Okay. Now, the last part here is to change to a conditional form. Okay, conditional statements. So the general form is like this: for all x, if px, then. So we have the if then. Okay, this is what I'm talking about. The if then. This is universal conditional. Universal, and there is if. So basically, we're going to start reading from here. If, okay, then you go to the left, and then you go to the right. Okay, so if you see if, and you have universal, you start reading from if, go to the left, then go to the right. So for example, we have like this: for all x in R, okay, if x greater than 2, then x squared greater than 4. How are we going to read this? We're going to start reading from here, go to the left, and then go to the right. So if a real number is greater than 2, then its square is greater than 4. So if, and then the domain, okay, then go to the right, simple. So see, if a real number, this is R, is greater than 2, then its square is greater than 4. You can read using this technique also whenever, okay, it's up to you, but the best is the first one. Okay, that is how to read if you have universal conditional. So this topic is about universal conditional statements. Conditional because we have if. Okay, so let's try to do the opposite before we go. This one, this 3, then we will go using this form. This is what we call as universal conditional statements. We have if a real number is an integer, then it is a rational number. How do we change this into this form? So using that form, we have to start with this. Simple. Yeah. X. It is a real number. Right? So basically, you can start from if here. If a real number. So this will be a real number. Because as I said, you do like this. If a real number, okay, comma here, is an integer. So x element of integer, then x is what? Element of rational number. So rational number is q. Z is integer, q is rational number. So you don't need to define this. It has its own letter q. Real numbers are real numbers. These are very famous in mathematics. Okay, so that's the answer. So basically, we are changing from English to this form. If a real number is an integer, then it is a rational number. Okay, it's here. If a real number is an integer, then it is a rational number. That is how to translate the first one. Here, all bytes have 8 bits. So for all x, if x is a byte, then x has 8 bits, following this form. For all x, if x is a byte, then x has 8 bits. Okay? Now here, for all x, if x, we always start with if, okay? If x is a fire truck, because no fire trucks are green, it means all fire trucks, change the sentence into this form. All fire trucks are not green, right? That means no fire trucks are green. So for all x, if x is a fire truck, then x is not green. Okay, so that's all for today. I want you to try to repeat this again, watch the recording, and try to master. So your midterm exam is until here. From number systems until predicate logic. So next week, I'm going to have the revision, all revisions only. So next week will be full revision. You should not be absent. From number systems until this topic will be revision next week. Okay, so the revision file is already on the move page. What is this? This one. So you have to scroll down until topic 4. What I discussed today is here. Quantifiers, universal and existential. You can open this and look at all the exercises. All the answers are there. Now your midterm revision file is here. Okay, this is from the beginning until the end. This is like the sample of your test. You have multiple choice, and solving and drawing. So next week we will be discussing this in the class, and I might be giving also 1 hour support session, especially for referral students to, answer these questions and additional questions. Additional questions, because I might be giving something like this, but I will be asking you to find the adjacency matrix. How to find the adjacency matrix of this, for example. Here, to find the adjacency matrix, actually, just give me 1 minute for this. Okay, matrix means table. What you're going to do is to write all the points. So W, X, Y, Z. And here, repeat W, X, Y, Z. This is the meaning of adjacency matrix. Okay. So what we will do, we're going to look at all the points. For example, W is connected to, it's not connected to itself because there is no loop. If there is a loop, you're going to put 1 here. So 0. If I'm going to draw a loop here, you're going to put 1. Now W to X, yes, there is 1 line, so 1. W to Y, 1. W to Z, 1 line. That's the meaning of that. How many lines going to the other points? Now X. X to W, yes. Okay. X to X, 0. because there is no loop here. X to Y, there is no line, or there is a line. This one is going to Y, right? And X to Z also. Okay. Next, Y is connected to W one time, is connected to X. It's not connected to itself. There is no loop. It's connected to Z. Z is connected to W. And then you have Z is connected to X. Is connected to Y. It's not connected to itself. This is the meaning of adjacency matrix. Matrix is a table, and you're going to have, the count, how many times it's connected there. Let's try this one. For example, this one has a loop. Okay, let's try this. This is very interesting. Assuming that this is the given. Okay, we have a loop here, for example. Guys, how many points do we have here? 1, 2, 3, 4, 5. This is the adjacency matrix of the graph. First is to write all the points, V1, V2, V3, V4, V5. Here, you're going to repeat 1. You have, this one should be space. V2, V3, V4, V5. So whatever you put here, left to right, same up and down. Okay, V1 is not connected to itself because there's no loop here. V1 is connected to V2. Okay. Is it connected to V3? There is no line going there. V4, yes, one time. V5, no. So you can see 1 plus 1, 2 is correct. Going to 2 and going to 4. Going to 2, going to 4. How about V2? Who can tell me?
Yes, Mr.
V2?
With V1?
Yes, V2 is connected to V1, correct?
And with V3, one line.
Okay.
And with V4?
Okay. Only 3, right?
Yes.
0 here because there is no loop. V5, there is no line going to V5. So 1, 2, 3 is correct. 1, 2, 3. V3 is connected to what? V2.
V2.
Just V2.
So this will be 0. V4?
With V1, V2, V4.
And V4, very good. Because loop, right?
Yes.
So 1, 2, 3. V5?
0.
So this will be, this might be part of your test. The name is adjacency matrix. Okay, so the revision file is ready. It is in the move page. As I said, it is here. Midterm revision files. Go to topic 4. Here, this one. Open this one. Okay, the answers also there, but I'm going to discuss this in the class next week. Okay, so do you have any question? We discussed all the topics already. Watch the recording again. Okay, guys, can I leave you now?
Thank you. Thank you.
Thank you, Basil. Thank you. Bye-bye.
Thank you, sir. Thank you. Thank you, Mr. Albert.
Thank you, Muhammad.
Thank you, Mr. Alba.
Thank you, Saif.
Thank you, Mr.
Thank you, Ivana.